The previous video I covered for you the first 2 points. In this video I'll cover population inversion and explain how a laser works. A laser is a source of energy because it contains a lot of light collimated in the same direction. So naturally you must pump in energy to allow it to give out energy by the law of conservation of energy. So what is pumping? It is a process which is deliberately added to the system to cause many atoms to transit to excited states. So at normal temperatures, most atoms are in the ground state with a negligible number in excited states. If you send in light of suitable wavelength, you can cause the electrons to excite from the ground state through stimulated absorption and move on to the excited state. This is pumping. Pumping can be achieved in many ways. First is what we have seen in the example, which is exposing the atoms to light of exactly the required frequency. We will see this in the Ruby laser later. Next, we also can cause this through collisions between molecules, which is shown later in the helium neon laser. Or we can do this by electrical charging. Why does two levels of energy not work? Well, the rates of stimulated absorption and stimulated emission is proportional to the number of atoms in their respective initial states. This means that we want a large number of atoms in the excited state so that there's more stimulated emission than stimulated absorption. However, with two energy states or two energy levels, regardless of how high your ambient temperature is or regardless of how much pumping you give it, there will be an equal amount of atoms in the excited state and in the ground state. Hence, this will mean that there will never be a net production of photons. Since there's no net production of photons, a laser cannot be formed. Hence, we require three energy levels. We call the ground state E1, we call the excited state E2, and we call the middle level a metastable state. The normal energy levels have a very short lifetime of 10 to the power minus 8 seconds, whereas the metastable state is a state which is stable, or metastable that we call it. It has a lifetime of actually only 10 to the power minus 3 seconds. Although it is small, it is much larger than that of a lifetime, of a normal lifetime. In fact, it is 10 to the power 5 times longer. Hence, we allow more atoms to be formed at this level. Right? Once again, for three levels, we not only need just three levels, we need a metastable state, and we want preferably the middle state to be metastable. Okay? Because of this metastable state, more electrons, right, will be stored in this state. Right? More electrons will be in this state, which means that it can store these atoms more, which will allow the functioning of the laser, which I will explain in the next few slides. So the presence of a metastable state allows for, this is a key term that I'm introducing to you, population inversion. Population inversion is a condition in which the number of atoms in an excited state exceeds the number of atoms in lower energy states. That means there are more atoms in energy level E metastable over E1. Right? If you look at this diagram, you can see very clearly that there are 5 atoms in the excited metastable state compared to a lower energy state, which is here, the ground state. This allows for a rate of de-excitation to be greater than the rate of excitation, hence producing net photons. Hence, through pumping and by having more atoms in the excited state compared to the ground state, there is a net production of laser light. This is a short animation to show you. We pump the atoms to the higher energy state, but it will drop down because of the short lifetime in the excited state E2. This is repeated for all the atoms. Right? Occasionally, an atom in the metastable state will fall back to the ground state. This is correct, and this will happen naturally. and this will emit a photon. But we'll continue pumping the rest of the states from the ground state. Here we see very clearly that population inversion has been achieved. There are now more atoms in the metastable state than in the ground state. This is of course an unnatural situation, which explains why lasers are not found in nature. But for a laser to work, we require just one more step. We need the working parts to amplify this light. And what do I mean? Here we see a real lasing cavity, and here we have a partial mirror, and on this side we have a full mirror. So we need to actually confine the laser photons and have optical amplification. When the metastable state de-excites and falls back to the ground state, it will produce a photon of energy. With population inversion, this photon is confined to the system, usually by mirrors. It will cause a chain reaction of stimulated emission from the metastable state to the ground state each time it passes through the atoms and interacts with them. Hence, the number of photons in this lasing cavity will increase rapidly. But what do I mean? Let me use some animation to explain. Here you see that these photons are excited. They can emit a photon by spontaneous emission. Look at all these photons, they are caused by spontaneous emission. This photon here is also spontaneously emitting a light photon, but however, because of the direction of travel is within the cavity, this will cause more stimulated emission of photons than the other photons that you see here. Also, because of the presence of a partial mirror, these light photons will bounce off the partial mirror and come back, which eventually will lead to this picture, having the lights bouncing forward and back, causing more and more stimulated emission. Once a suitable amount of photons have been accumulated, this partial mirror can be 90% transparent, if 90% reflective, will allow 10% of light to pass through, which means that for every 100 photons hitting it, 10 photons will exit. So here we see that the stimulated emission occurs when the correct photon enters and de-excites the electrons in the metastable state. Okay. While some are de-excited, some photons are actually lost by exciting back the electrons to the metastable state. Although we do not want this is hard to be prevented. Right, each time a light photon passes through the collection of atoms, a larger number of photons will be created. So the intensity of light laser increases, and this is why it's called light amplification by stimulated emission of radiation, which is again the acronym for laser. Now let's look at another animation to show how this is done. First, we use external light source to optically pump the light to a excited state. Now I group all the excited states in the center and show what happens. First, two photons are emitted through spontaneous emission, but when they rebound from the mirror, it causes more and more stimulated emission. Let's look at that again. Two photons are emitted. When it bounces back, it stimulates emission and causes 4 photons to exit. This 4 comes back and stimulates 8 to exit. This process repeats again and again to cause laser to be formed. So let's have a summary. First, you must have pumping to bring energy to the atoms, to pump them from the ground state E1 to the energy excited state E2. Once they reach the excited state E2, most of them in fact, because of short lifetime, will fall to the metastable state, and they will be accumulated there because of the long lifespan of the metastable state. This causes population inversion and have more atoms in the metastable state than the ground state. This confinement of laser produces some metastable states. This confinement of laser produced by the metastable states, when they de-excite, causes a chain reaction of downward transition from the metastable state to the ground state. Hence, this increases rapidly the net production of such laser photons. And population inversion ensures that there will always be a net production of such photons. And of course, lastly, you must also have this light in a laser cavity. Right, we have reached the end for this section. I'll explain the lasers in the next part. I'll give you some examples of lasers in the next part.